earliest humans set out in boats in the Pacific Ocean and the Atlantic Ocean just to figure out what was out there. And, then like later, tens of thousands of years later, humans set out into space to explore things. This is no different. It's just that you're trying to understand and explore the universe that we live in just by collecting data and understanding it.
I am currently with Associate Professor in Astronomy, Desika Narayanan. His research focuses on theoretical models and primarily related to cosmological, galaxy evolution, star formation, and interstellar medium. Would you say it's more aligned with astronomy, astrophysics, astronomy, right?
So there's not really much of a distinction between astronomy and astrophysics. Historically, there was one where some people would look at the night sky and say, this is where planets are, this is where stars are. And that, I think, is what you would maybe define as astronomy. But that's really an outdated method of studying the skies. And now everything is really astrophysics. It's the application of physics to the cosmos.
Okay, maybe you could call astronomy the people that are still just looking at astronomers, just looking at the sky for recreational, maybe.
Exactly. I think that'd be a reasonable way to divide it, whereas the researchers are doing astrophysics.
Interesting. Okay.
Yeah.
So yeah, maybe we can just get started. So first question, what is a star? Like when we're looking at the sun, we've been told it's the star, but I don't think anybody has... of course not anybody, but I don't think the majority of people have a solid understanding what a star even is.
That's a good question. That's funny because it's so fundamental to astronomy that you don't think about the fact that everyone sees them in the night sky and yet doesn't think very carefully about what they are. So a sun fundamentally is a giant ball of gas. It can weigh a ton. I mean, I'd have to think how much more than the Earth it weighs, but I think it's something like, if I had to guess, 100 billion times as much as the sun, or as the Earth. So
that's not really a number that our heads can wrap
and
around,
that's an important thing, right? So in astronomy, we're regularly dealing with size scales and masses and distances and time elapsed that will blow your mind if you think about it. For an example, I was just in a talk earlier today before you came in here, and someone was quoting a very short time scale of 10,000 years. And in my head, I was like, oh yeah, in astronomy, that's a microscopic time scale in astronomy. And then in my head, I was like, 10,000 years ago on Earth, people? I didn't even know what was going on 10,000 years ago, right?
I think it was
ancient civilization or something.
Humans starting to
so, if you think about 10,000 years from now, it's a huge amount of time, but in the cosmos, it's nothing. So, and you have to kind of put that stuff aside when you're thinking about astronomy and just think about the numbers as numbers. And then, so one of the fun things about this is that even professional astronomers like myself, we still get a kick out of watching things like on Nova or these specials like this, because on the day-to-day research, it's all just numbers, and you're not really thinking about the coolness of it and the magic of it until you sit back and watch some cool documentary someone else has done as well. Okay, so back
Cosmos type of thing.
Exactly. So back to your original question, what is a star? So it's a giant ball of gas. It's so massive that it's held together by its own gravity. So a cloud, for example, is not big enough to hold together by its own gravity, but it is just a big ball of gas.
Yeah, and it's the same concept, right? Like just some particles can attract it, and then there you have it. Like your cloud that we can see in the sky.
Exactly. So what happens is, it may be easier to think about what a star is by considering how they're born. So in space, you have these giant clouds. Like literally they look like clouds outside the sky. And they're something like 1 million times the mass of our own sun, 100,000 to 1 million times the mass of our own sun. And these clouds are we call them stellar nurseries, because this is where many, many stars will be born. Now, just like if you look at a cloud in the sky, you'll see some parts are a little darker, some parts are a little lighter. That means, and some parts are wispy. And if you fly over a cloud in a plane, you'll see that there's some parts where there's just more cloud and there's some parts where there's less cloud. Just like that, clouds in space, there's some parts that are denser and have more mass and some parts don't. So what happens is the parts that are denser eventually begin to collapse, that they can't hold themselves up anymore. And they begin to collapse due to their own gravity. And they keep collapsing and collapsing and collapsing. And eventually what happens is that you need something to hold this thing up, right? Otherwise, it's going to keep collapsing. So what eventually holds it up is once it collapses enough, the hydrogen in that cloud, 2 hydrogen atoms will smash together, and those hydrogen atoms, when they smash together, they'll fuse. And this is the same process that goes on inside an atomic bomb. And so when they fuse together, what happens is 2 hydrogens, each of them weigh, let's say they each weigh 1 in some unit, an atomic mass units. Well, if you have one hydrogen and another hydrogen, and they each weigh 1, and they smash together to form a molecule, you would say, well, or if they smash together to fuse together, you would say, oh, they must weigh 2 because 1 plus 1 equals 2. But they don't, right? So what happens is 1 hydrogen plus 1 hydrogen, each of them weighs 1. They'll smash together to make helium, but helium doesn't weigh 1. It weighs it doesn't weigh 2. It weighs like 1.99999 or something, right? And so that mass has to go somewhere. And where that mass goes is the famous equation E equals mc squared. That mass turns into energy. And what happens is that energy then is light, and it comes back out of the star. So if I take 2 atoms and I smash them together like this just on Earth, I'll produce some energy. And if I take a bunch of atoms, I'll produce a lot of energy. And that's how you make atomic bombs. In the sun, it's the same situation going on, but it's tons and tons and tons of hydrogen atoms smashing together in order to make basically the biggest atomic bombs in the universe. And that's what's firing up the sun, and that's what's producing all the energy, all the light, all the heat that we get. Okay. So, we oftentimes say the phrase something like the sun burns, but it's not really burning. It's not combusting like if you burn wood in your fireplace. It's actually fusing hydrogen into helium. And
more like an explosion, maybe?
Exactly. That's a much better way to think about it.
Okay.
Except it's a series of explosions that in our sun's case will go on for 10 billion years.
Right.
Okay. So it's a long time.
And one of the questions would be why does it collapse? And what does it really mean collapse? Because you're saying it comes close together until it collapses. There's maybe a threshold or something like that. So what is that process?
Yeah, the way to think about it is imagine I have a cloud out there, and imagine that one part of it's just a little denser. So it's dense. So what's holding the cloud up, right? There's gravity is always pulling it in. So something must be holding it back apart, pushing it back apart if you want it to stay still. Mm-hmm. So what's pushing it apart is its own thermal energy. Everything that has a temperature has an energy associated with it. And so basically that temperature is if you think back to high school chemistry, PV equals nRT, that equation you learned, that temperature has a pressure associated with it. So that's pushing back against the cloud. Now, the cloud has some temperature, so it has some pressure. Imagine I keep dumping more and more cloud on top of that cloud. Well, eventually, the gravity will get to be so big that the temperature can no longer hold it up. And so then it'll start to collapse in on itself. And when it collapses in on itself, that's when eventually it'll get so dense that you'll get the nuclear bombs going off. And then those nuclear bombs provide so much energy that they stabilize the cloud against collapse, and it just stays still. So you get just enough balancing of the nuclear energy pushing out as the gravity pulling in, and so we call that hydrostatic equilibrium, and that's where the star basically just sits in equilibrium at the more or less the same size and mass for 10 billion years.
Yeah, so it could be kind of like a balloon, right?
Kind of like that.
A balloon is trying to expand because of its own pressure, and the rubber, which maybe could be the gravity, it's holding it together.
That's a great example. Yeah, exactly.
Okay.
A great analogy.
Thank you. And we'll come back to the star formation and why it's important and everything. But I first wanted to dig into how do you know a star is there? What are the means of studying this thing? What needs to happen so that you can know, oh, this star is doing this thing, or...
So you're touching on a complicated question in astronomy in general, and this is that we rarely see things happen. And the reason we rarely see things happen is because the timescales are so long. I just told you about this very, very short timescale of 10,000 years. Well, obviously, I'm not going to be alive 10,000 years from now. So now if you think about longer timescales, I told you the sun will live 10 billion years. Well, I'm not going to be alive 10 billion years from now either, so how do I know that? So in astronomy, the way we figure things out is you catch many, many different things at different instances of their lives. So an analogy to this would be, imagine you were an alien civilization and you were able to take just one picture of humans on Earth. Just one. Well, you don't get to see humans go from baby to teenager to grown up to old person to dead over, let's say, 100 years.
Mm-hmm.
So if you're an alien, how are you going to figure this out? Well, you start to see things like connections between things, because you have one picture, so you do have pictures of babies, you do have pictures of teenagers, you do have pictures of grown-ups, you do have pictures of old people. So you can start to maybe see the transitions between those and create an evolutionary picture. Then you could ask yourself, well, fine, how long do humans live? Well, I better find some way of age dating those gray people who are walking around, and I age date them in some way, and I say, well, they're 100 years old, and then there don't seem to be people past that, so it must be that people live to about 100 years and then they die. And so you play the same game with stars, or anything in the universe, really. And there's complicated ways of age dating things that, to be honest, I'm not an expert, and I'm not really very clear on how the age dating works very well. But you play games like this where you see stars across different evolutionary phases, and when you combine that, so astronomy in general, it's constantly an interplay between people who are observing things and trying to figure things out, and then theoretical researchers who are using equations and computer code to figure things out. And then there's an interplay between the two of them. So the observers construct some scenario based on what they think is happening observationally. And then the theoreticians will say, well, yes, actually, this is explainable by these equations or these computer simulations. And then you think, well, maybe this is a plausible scenario for what's happening for the star. And the theoreticians might say, if we're right, you'll also observe this other thing that you haven't yet observed. And the observers will go test that and say, oh, yeah, we do actually observe this. So maybe this whole scenario is right. And we sort of iterate like that to figure out what's happening.
Right, and it's a interplay between this makes an advantage and maybe this catches up and then this one advantage. So it's got, what I'm trying to say is that it's not always one feeds the other, right? It's kind of like both, because I was going to ask you, like, where does the theoreticians come up with their stuff?
So, in my opinion, it's generally an observationally driven field. In that the observers see things, and usually the theoreticians are catching up to figure out what could be happening. But that's not always the case. I mean, there are certainly many, many times theoreticians have predicted something, and then the observers, could be decades later, figure it out. One of the most famous examples of this is the concept of dark energy in the universe, which is forcing the universe to expand at an accelerating rate. Einstein came up with this in I don't even know when, like the 30s or 40s, I 50s, I don't even know, a long time ago, right? And they only, observers only really observationally confirmed this in the late 1990s. And so sometimes it will happen that the theoreticians come up with something first. And that's always the most powerful thing you can do. Explaining something after the fact is a little bit, it's important and interesting, but we call that post-predicting. It's much more important to predict, because if you predict, then it's a very powerful statement. I'm saying, given no other information, I am predicting that you will see this. And then if I'm right, then maybe this scenario I've painted is correct. And so oftentimes we try to make predictions when we can.
Right. And I think it's also important to distinct that, there's two different people. Like, right, there's the experimentalist that it's maybe just the one that observes, collects data, tells you what's going on, and there's the theorist that analyzes whatever data is and tries to come up with a model that explains that data.
Yeah, that's exactly right.
Right, and there's avenues for it, but for example, you mentioned the Einstein's thing. Was Einstein? He was probably always having conversations with experimentalists and always getting data and refining his things. So it's always like a feedback loop between the two.
I think so. I mean, in Einstein's particular case, I'm not sure, because back then the state of observations were not as good as they are today. But nowadays, certainly that's true. Nowadays, at conferences, you intermix the theoretical talks and the observational talks, and you try to have a constant interplay between the two. in order to understand what's happening.
Right. And I think people normally have a better idea of what the theoretician looks like day to day. It's kind of like pondering. It's like, oh, this would be this, and just going to their whiteboards and start writing. So what is the role of the experimentalist? How exactly do they get their data? Because I wanted to, the question that I asked you before of like, what is the main tool? I wanted to get to the main thing that you get for your field, which is kind of like light. Yeah. Right? Like you mentioned it's observing. Yeah. Right? So why is that your only tool, and why, and yeah, first, why is that your only tool?
Well, that's a complicated question. So the first thing is, until about 5 or 6 years ago, light was the only tool we had. Maybe 7 years ago now. All right. So for all of humanity, light was the only tool we ever had. And that's because we can't fly out into space and easily get to things. I mean, it was such a challenge. The nearest object we could possibly get to is the moon. And it was such a challenge for humanity to get to the moon. And we've never been further than that, right? Mm-hmm. I mean, we've never even been to Mars. So now you're talking about things that are, billions of light years away. We could never get to them. We can never fly outside of our galaxy to see what's happening, not on human timescales. And so because of that, all we can do is just, set up telescopes, which are big buckets, to collect light and get that information. Now, the one thing that changed like 6 or 7 years ago was the detection of gravitational waves, right. which is you can think of it like light that's emitted by gravity. When two objects interact gravitationally, they emit gravitational waves that we're able to detect from very massive objects like black holes or neutron stars or things like that. So we call that multi-messenger astrophysics, and that's actually it's called that because it's the other messenger. There's light as one messenger, and gravitational waves is now the other messenger giving us information. UF is a huge player in the gravitational wave game. In the physics department, there's a ton of people working on gravitational waves and doing really exciting stuff.
And for exploring stars and galaxy formations, your main tool is light. But yes. Why is it that important? Like, isn't it just you see a pretty color in the sky and you see, oh, that's yellow. That's pretty.
I see what you're saying. So there's a lot of really interesting physics behind that light. So for example, hotter objects emit more light in the ultraviolet and in the blue. Colder objects emit more light in the red. You can,
which is like what is ultraviolet and what is red?
Oh, sorry. So like ultraviolet are very short wavelength, high energy light. It's like the light that comes from the sun that gives you skin cancer or sunburns. And then infrared light, which is very long wavelength light. So this is if you think about like the rainbow, our eyes see in a very, very narrow range of light wavelengths. We see red, orange, yellow, green, blue, purple, right? And so purple is the bluest of the light that we can see. But beyond that, there's plenty of light that's even bluer than purple, like ultraviolet light, and then even like X-rays are just a form of light that are even shorter wavelength and higher energy. So very hot things in the universe emit in the ultraviolet, and very hot things emit in X-rays. At the other end of the spectrum, if you go, purple all the way down to red is the lowest energy light that we have. And so you can actually think about this. If you imagine think about a lighter is a bad version of this, but like a blowtorch is a good version of this. If you think about what a blowtorch looks like, when the flame is coming out right near the tip where it's hottest, it's blue and purple. And then as that flame gets further and further away from the blowtorch, it's red, like orange and red. That's because it's cooling off. So as things cool off, they shift in their light from purple to red. And then it actually shifts even further into the infrared, but we can't see in the infrared with our eyes. Some animals can, but we can't. And then it can even shift further into the radio waves. So like the radio waves are literally the same things like your cell phone or radios in your car get. It's a radio. So
this is like a cool topic, and it's not really straightforward, right? That there's this thing that exists, and this thing is this thing is how we see it, right? Like we get this thing, it interacts with our eyes somehow. and we get these pretty colors. But there's also this thing in other forms that can interact with you in many, many ways that you cannot really see. So we would need instruments. There. Yeah,
exactly. And it's there all the time. So, and nothing is emitting just one type of light. So here's an example. Our sun, the nearest star, the surface of it is 5,000 degrees. 5,000 degree light happens to emit most of its emission in the optical, red, orange, yellow, green, blue, purple, which is what we see. So humans naturally have evolved over time to see primarily in the optical. The sun is also emitting other wavelengths that we don't see. It's just not emitting as much of them. It's emitting ultraviolet light. That's why you can't go outside without sunscreen, because that ultraviolet light is high energy light that burns your skin. It's also emitting infrared light. We can't see it. It also doesn't really do anything to us because it's low energy. So everything, you yourself right now, because you are a cold object relative to things, like you're like, 500 Kelvin or 300 Kelvin or something, most of the light you emit is actually infrared. And so I can't see you in the infrared. All I can see is the optical lights from these lights in this room bouncing off your skin and hitting my eye, because my eye sees in the optical. But you are actually emitting most of your own native light in the infrared, as I am. So if I shut off all the lights in this room, if I had infrared goggles on, I could see you. And that's what night vision goggles are. Night vision goggles allow us to see in the infrared, and they allow me to see cold objects like people and animals at night, even when there's no optical light to hit them and bounce into my eyes.
Right, and there's also, I've seen ultraviolet lenses that you can actually see when you put sunscreen, that it gets totally dark.
That's cool. I've never seen that.
Yeah, it's pretty cool, that's the reason, because you think of I'm just putting this cream that is just dirty and yucky that you put in your skin, doesn't do anything, right? But when you actually see an ultraviolet, you put your sunscreen and your skin looks way darker.
Oh, that's cool.
Because you're not seeing any of the ultraviolet light getting reflected. So it's pretty cool. So and just all of these concepts can tie up with maybe one of the big events that people have been paying attention recently, that was pretty big, of the James Webb Space Telescope, right? That now it's this big telescope that NASA put into space, that it will be really useful for people like you, I would assume.
For sure.
And it's a big deal because it can now, you can see. Oh, you tell me, why it's a big deal?
Sure, I'll tell you. So the James Webb Space Telescope actually is built to detect infrared light. Mm-hmm. So what that means is what it sees, we cannot see with our eyes. Now, here's the problem. Like I just mentioned to you, you are a cold object. I'm a cold object. Everything on Earth, more or less, is cold. So most of the light we emit is infrared. Mm-hmm. So you can't have an infrared telescope on the Earth because it's too noisy. There's light coming from everywhere, and you're trying to get rid of all that light and just look at the cosmos. So you have to go to space to get away from all the noise of the Earth. That's reason number one. Reason number two...
And before you go to reason number two, it's still not super... So you're mentioning we're cold objects, and therefore we emit most of our light in infrared. Wouldn't it be if we're hotter objects, we get more? In my intuition tells me the hotter, the more infrared would I.
So hotter is bluer. And purple, and then colder is redder. Okay. So the way to think about the rainbow is red, orange, yellow. Mm-hmm. If you start with red, that's the coldest, and you go red, orange, yellow, green, blue, purple. You go from colder to hotter.
Right. I know. You were talking about
we tend to put our temperature faucets red is hot and blue is cold. Yeah. But in reality, it's the opposite. Blue is hot and red is cold.
And the blowtorch is a good example of it.
Yeah, exactly.
Right. So continue. I'm sorry.
Okay, so reason number one is that the Earth is a huge source of background noise for infrared. Reason number two is that actually there's a ton of water vapor in the air. I mean, especially in a place like Florida. And that blocks out a lot of infrared light. And so that keeps you from being able to easily observe in the infrared from the Earth. So you put these telescopes in space. And in fact, James Webb Space Telescope, JWST, has gone to a place called L2, which is a stable orbit in space, but it's far away from the Earth. So that way you can minimize noise from the Earth, but still have it be sort of stable in the Earth, Moon, Sun orbital configuration.
Maybe a good way to think of it is if you don't put it in that specific location relative to the Earth, it would kind of like wiggle around a lot.
Exactly. And you're trying to minimize that because you can only send so much fuel with it, and once you run out of fuel, you're done with the telescope. And so you're trying to minimize how much it can wiggle, and so you want it to stay as stable as possible.
Yeah.
So the James Webb Space Telescope is designed to work in the infrared, and it's fundamentally designed to look for, mostly for cold things in the universe. So planets are cold, the atmospheres of planets are cold, the gas inside of galaxies and dust inside of galaxies that make these giant clouds that form stars are cold. And then the other important, so locally, that's what James Webb Space Telescope is designed to do. Now, the other key piece of information that we haven't talked about yet is the fact that the universe is expanding. So the universe is just getting bigger and bigger and bigger and bigger and bigger every second of every day of every year forever. So now imagine you're standing on just like the surface of a floor. And imagine it's like a checkerboard floor or something like that, right? Mm-hmm. And so you can see the checkerboards. And now imagine that the floor starts to expand like a balloon surface. Well, as that does that, then the checkerboards are going to expand too, right? Space itself is expanding.
Like the squares are becoming bigger and bigger.
So what that also does is when you have light in the universe, that stretches out too as the universe expands. So when light stretches out, it changes the wavelength of the light, and it changes it from bluer to redder. So even though it's not the object that emitted it is not actually getting any cooler, the light as it goes through an expanding universe gets redder and redder and redder.
Right. So what we were talking about before is that we have like this spectrum of the thing which is light, and literally what changes in that spectrum is like the spacing between the bumps of the wave.
Exactly.
That's a simplified way to put it.
That's a great way to, and that's exactly what it is.
What is happening is that these bumps are literally getting expanded because the space is getting expanded.
Exactly.
It sounds like crazy talk, but
it is. But you hear that you experience this every single day. So, well, I mean, not every day, but many times in your life you do. So, and the concept is called the Doppler shift, and the basic idea is, imagine you're standing on a street corner and you hear a siren coming by and it's going to pass you. You hear it go woo, and it gets really high pitched until it hits you, and then right when it passes you, you hear it go woo, like that. And a train does the same thing. And so what's happening there is the same thing. As the sound waves are getting pushed toward you by the approaching siren, they get moved to shorter and shorter wavelength, and they get high pitch. That's the equivalent of getting bluer. So it goes whoop, and then it gets further away from you, and they start getting stretched out, and it goes whoo. And so light does the same thing. Okay, so how does this relate to James Webb Space Telescope?
Yeah,
right? So James Webb Space Telescope is designed to see infrared light, which sees cold things in the local universe. But also, imagine I'm at the very distant edge of the universe, 13 billion light years away, and I have a hot star, 10,000 degree star, that's emitting most of its light in the ultraviolet. Well, over the 10 billion years it took for that light to go from that star to hit our telescope, that universe has expanded quite a bit. And now that ultraviolet light has got stretched out until it's so red, it's in the infrared. And you couldn't see it in the ultraviolet if you wanted to. You would see it in the infrared. And so by looking in the infrared, it's a great way of finding stars and galaxies that formed at the very beginning of the universe in the first, 50, 100 million, or 100 to 500 million years after the Big Bang, which are the very first stars and galaxies that ever formed. And so it's taking advantage of the fact that even though the light they emitted was in the ultraviolet, it's getting stretched out all the way into the infrared, so it's detectable there by James Webb Space Telescope.
Yeah, that's why we saw the really cool pictures of like this gigantic thing that if you zoomed and zoomed and zoomed, you see all the stars that are really, really, really far. And they said, oh, you can see a star that was from the beginning of the universe.
Exactly.
So that can kind of go towards that route of you're looking at all this process in the sky, right? Like you point your telescope, a bunch of stuff is happening. If you go back in time, like how do you go back in time? Like, because you said that we can get different snapshots, right? After we have the different snapshots, we can have some sort of idea of how things progress over time. And if we have that idea, we can not only go to the front, we can go to the past.
Exactly.
So can you tell me that story?
Yeah, sure. So one easy example of this is studying how galaxies evolve. So galaxies are big collections of stars. You're familiar maybe with our own galaxy, which is the Milky Way, which is a big collection of stars. And that's basically like the neighborhood of houses we live in. But there's other neighborhoods, there's other galaxies. And they've been forming and evolving for the entirety of the universe, which is 14 billion years. Now, the thing is, light that is emitted from the stars and galaxies has a finite speed to it. It's like 3 times 10 to the 8 meters per second or something like that. 3 times 10 to the 5 kilometers per second. Light goes super fast. Mm-hmm. It's super fast, but it has a finite speed. And so if you're going 3 times 10 to the 5 kilometers in a second, well, it can take you 14 billion years to cross the entire universe if you were emitted soon after the Big Bang was born or happened. So galaxies that formed 13 billion years ago, that light has been traveling in space for 13 billion years before we see it. So now imagine that there's a baby, and this baby is across the room from across the universe from you, and the baby shows light on its face, and then that light takes 100 years to get to you. What you're going to see, the light you're going to see is going to be the picture of the baby now, the light you're going to see is the picture of the baby as it's shown the light on its face. So you're getting a sense of what the baby looked like 100 years ago.
Right, just because of the fact that light takes time to get
exactly. So you're not actually seeing the baby as it is now today. You're seeing the baby as it was 100 years ago when it put the light on its face. So the same thing is true of the galaxies. The galaxies emitted this light 13 billion years ago. So we aren't seeing what they look like now, today, 13 billion years later. We're seeing what they look like when they were infant galaxies 13 billion years ago. So like that, we start to construct images of what scenarios of what we think happened. So now imagine I have the baby and it shines a light on its face 100 years ago. I have a teenager that shines a light on his face 90 years ago. Mm-hmm. And then I have a middle-aged person shines light on his face 50 years ago. And then I have an old person who shines light on his face yesterday. Mm-hmm. Right? And so I get pictures of what people look like, humans look like, at various stages in their evolution. The same thing happens with galaxies. I can look at galaxies in the beginning of the universe to understand how some of the earliest galaxies may have formed. And then I can look at galaxies not so long ago to understand how galaxies that are middle-aged look. And I can look at galaxies today to see what the remnants of those galaxies look like. And we can start to try to construct physical scenarios for what governs the evolution of galaxies as the universe expands and evolves over time.
And that is what you're interested in.
That's specifically what I work on, yes.
Okay. And how does that look like? Like you're getting some sort of data of this many snapshots that you're talking about?
Well, so
you combine them together and what?
Observers do that.
Exactly.
So observers do that.
Yeah.
So I myself am a theoretician. So right. I write all computer models based on trying to understand what the observers are seeing. Mm-hmm. And so we write big computer simulations that use the Hypergator supercomputer here at UF to try to understand how galaxies were formed, in the first couple 100 million years after the Big Bang, and how they evolve over time to look like they do today.
Right. And how does, why, you mentioned the supercomputer, why would you need such a big computer?
Well, it's a great question. So think back to high school physics, and you learn something like the equation F equals ma or something, right? Mm-hmm. So in high school physics, you learn F equals ma, and if I give you a couple of variables, you can work that equation out by hand. It takes you 2 seconds, mm-hmm. right? So then maybe you have a calculator and it takes you 1 second. That's one equation. Now imagine I ask you to do F equals ma for 1 billion things. Well, fine. It's going to take you a little longer than a few seconds. It might take you 1 billion seconds, but you can do it. It'll just take you a while. Now imagine I ask you to do F equals ma and 1,000 other equations on 1 billion different particles. Wow, it might take you a very long time. It might take you millions of years to do this by hand. So a supercomputer is just doing all of these calculations that you could do by hand, but there's just so many trillions and trillions of these calculations that you couldn't possibly do them on hundreds of humans' lifetimes. And so you employ the use of many, many computers all working at once on the same problem in order to, tell you what you need to know.
Right.
So the problems are, substantially more complicated than the simple F equals ma that you learned in high school physics, but it's the same basic idea. You're solving systems of equations that tell these particles or fluids or whatever, stars, whatever you're studying, what to do. And then you study what happens in these computer models.
And you can go a little bit in more detail if you want to, because I'm curious about it too. Like, so what those equations look like? Is it still like some sort of F equals ma, like in a bigger scale, like a systems equation? Or you mentioned that you might have some sort of like, you mentioned fluids, right? So
right.
Like, why did you mention fluids if it's just particles?
Because,
there in
well,
space?
so there are many types of interactions that we worry about in space. So there is gravity. So you have the gravity equations you learned about in high school physics, like Gm1 m2 over r squared. You might remember, you might not. And you have acceleration. I guess that's really, the same idea. Then you also have to worry about the equations of fluid dynamics. And that's because most of space is gas. And the equations that govern gases are the equations of fluid dynamics. So you have to worry about the equations of fluids because that tells you how things like temperatures and pressures evolve across different gases in space. You have to worry about the equations of what's called radiative transfer, which is how light goes through space. Because light not only is your messenger, it tells you information, but it also can actually impact the physical system. Light has an energy associated with it. So if it hits an object, it pushes that object. And so we have to worry about that. We may have to worry about the equations of electrodynamics and magnetic fields because there are large-scale magnetic fields in space that can impact things. So there's various equations like that we put in to the simulation, and that really is the art of writing these big numerical simulations to describe the universe. Is to figure out what equations to put in that are important. Now you might ask, why don't you just put in all the equations and simulate everything? Well, I can't put in all the equations because, well, first of all, I don't necessarily know all the equations. But even if I did, I can't put in all the equations because all of the equations would mean the quantum mechanics of what's governing atom flows inside of things. And you could say, fine, why don't you just simulate all of the atoms in the universe? The reason is because there is one supercomputer that is simulating all of the atoms in the universe, and that is Mother Nature. We cannot simulate things any faster than Mother Nature is currently doing it. And so if I'm trying to do things on human timescales, not cosmic timescales, and so I have to make approximations. So, for example, if I'm trying to simulate a galaxy, I might simulate it with a bunch of different particles that represent solids like stars, well, things that we consider solids like stars, even though they're really gas. Some might simulate actual big gas clouds or represent gas clouds. And I might have 1 billion of these particles representing a galaxy, for example. So if I have 1 billion of these particles representing a galaxy, that means each particle that represents a star really represents like 10,000 or 100,000 stars at once. So I have to come up with approximations for how 100,000 stars act at once instead of just one star acting at once. And so there's a big art to this of trying to figure out what equations do I use and then what approximations can I use in order to make my simulation actually complete on human timescales and still learn something. Because if I make huge approximations for everything, well, then I don't learn anything.
And how do you get good at this art? And like, how do you know that your art is good?
That's what we do in the PhD program is we learn this. So you oftentimes don't know, and so you have to do sometimes numerical experiments where you increase the resolution and you therefore, or you decrease the resolution and you figure out, am I learning new information or am I not learning new information? So you can imagine taking a blurry photo with an iPhone 3 a better photo with an iPhone 8 and then a much better photo with a DSLR camera.
Mm-hmm.
And you might find that the iPhone 8 was good enough and you don't get any new information from the DSLR. So then you don't use that expensive equipment that costs a lot of money and takes a lot of time. But the iPhone 3 was maybe no good. And so you do tests like this to figure out what sort of simulations and what sort of details do I need to make reliable answers.
And is there some feedback of, I run this, let me check real quick in the sky to see if it actually made sense what I did?
There is feedback like that. It's not as quick as that.
Right.
So there's two things. One is most theorists are not well equipped and experienced on how to use telescopes. Some are. There's some very superhuman astronomers out there who know what they're doing and are able to do both. I'm not, but there are some. So there certainly are some astronomers who both write their own theoretical models and propose for their own observations. But the other issue is how you actually get time on a telescope. You can't just go walk up to a $1 billion telescope and use it. You have to demonstrate that you have any idea of what you want to do. And as you can imagine, it's competitive. And so what happens is once or twice a year, every telescope will issue a call for proposals. And they'll say, send us a proposal. And for this, you're allowed to send a proposal. Anyone can do a proposal. And you write a proposal within the page limits that they say. And you say, I'm going to use your telescope to do this. And here's how I'm going to use it. And this is why this is important. And this is why this is necessary to advance the field of planet formation or galaxy evolution or something like that. And then a committee of your peers will meet and they'll evaluate all the proposals. And when they evaluate all the proposals, they'll rank order them based on, some combination of interestingness and feasibility. And then they'll basically go through the rank order and say, okay, the top 40 people can get their time and everyone else try again next time. So even if I have an idea and I want to test it, there's a limit in how much, how quickly that can happen because I have to wait for the next proposal cycle and then write the proposal and hope it gets accepted in the 10% odds and go from there. So it's a slow moving field in that way. But
maybe you could be more get your feedback from other places, maybe like historical data or something like that, right?
Exactly, and that's a great point. So a lot of telescopes will make their data public and after the fact, and so you can dig through the archives and find data that may help validate or refute your claims. And there's a large number of astronomers who specialize in dealing with archival data. And it's a really important thing, actually. I was on a bike ride with a friend of mine this morning, and I made the grand claim. I said, I think we could probably keep astronomy alive for quite a while just from archival data. Because there's hundreds and hundreds and hundreds of terabytes, probably petabytes of data out there that, we're human capacity limited. We don't have but so many astronomers out there working on data. So there's a lot of information out there, even in the data we still already have.
And I wanted to ask you also, as we covered a little bit of the details, you mentioned there's this committees where you apply and they ask you, why is your field, why what you're doing is important. So I wanted to ask you, why what you are doing it's important, and maybe if it's if there's an intersection there, or even if there's not, like why did you get interested in studying these types of things?
Sure. So in particular, I'm not going to tell you why it's important. I'm going to tell you why I think it's fun.
Okay.
So in particular, I study what's known as the interstellar medium. This is the gas that floats around in galaxies. So the giant clouds I was telling you about. The reason it's cool is because it allows you to work on so many different types of problems, because this gas eventually is what collapses to form into stars. Then what happens inside those stars is the elements, you start to fuse together hydrogens into heliums. Then you start to fuse heliums together into carbons. Then you start to fuse carbons together into heavier elements. And then eventually that star might explode and dump all that material back out into the galaxy, into the gas clouds. And then new stars will form. And so by studying this interstellar medium, and you can study the evolution of how galaxies evolved over cosmic time as more and more stars formed and processed these elements into heavier and heavier elements. And so you get a sense then of both, you get to study both how stars form and you get to study how this impacts the galaxy as a whole, because you get to study how these heavy elements are distributed throughout galaxies, all throughout cosmic time. And these, this is implications from everything from like the origins of life and organic matter throughout the universe, through just questions that plague humans over all of time, like where do we come from, and what's going to happen to us in the future. So I think it's if you ask, is it important? No, it's not going to keep your plane in the air, and it's not going to keep your iPhone working. But is it important for the sense of human knowledge? Well, I hope so.
Yeah, in a sense, that's important too, right? Like, that's important too. I would say, in a way, that's answering those questions is it's a way for us to keep doing what we're doing, right? Like, to keep wanting to do things.
I think so. I mean, I think it's a sad question to ask. What's the value of what good is it? And I get this question a lot. Like, what good is it for humans? And I think it's a sad question. I think that's like asking, why are you reading that Michael Crichton book? What value is that to you? Well, you're learning something. You're expanding your mind. You're thinking different. Who cares? Why? Just because you enjoy it. And I think that's the same
can be
thing,
important
right? Like,
in itself, right?
Yeah, like, I mean, do you like learning cool things? And it's a sad thing if the answer is no. I think that's one of the amazing things that we have as our society decided to value, just the exploration of thought and the world that we live in, just because we want to know. The earliest humans set out in boats in the Pacific Ocean and the Atlantic Ocean just to figure out what was out there. And then like later, tens of thousands of years later, humans set out into space to explore things. This is no different. It's just that you're trying to understand and explore the universe that we live in just by collecting data and understanding it. And it's amazing, right? It's amazing. If people wanted to explore how humans worked, even if it had no application for medicine and for the longevity of lives, it still would be cool. I still want to know how cells work and how osmosis happens and how the digestive tract works. That's still cool to know. And I think it's an amazing thing that we get to do stuff like this.
How would you communicate more of that, or how can you make sure that that message is felt by people?
I think as academics generally, and certainly in a field that is as publicly visible as astronomy, it's critical to disseminate your results, not just to experts. So yes, do I love going to conferences and talking really nerdy to other people who are very much in my field? Of course I do. That's wonderful for my own brain. But that's a selfish thing because it's just for me. I think it's really important for us to contribute to magazine articles. When a reporter calls, if someone calls for a podcast, to say yes, because it's important to share that excitement of what you've learned with the community. And we saw this when the JWST launched, and we saw the headlines on New York Times, etc., and how it captured humanity, how President Biden and the Vice President were in the room as the first images came down. I think cool. That's what your taxpayer dollars are paying for, right? Like it's important that if the person in the plane next to you starts asking you, that you don't just say I'm too busy, but you answer them and you talk to them about it, because that's they're paying for it. And when academics keep this information to themselves, I think it foments a lack of goodwill between the public, the taxpayer who's paying for this, and the academics who are the ones who are privileged enough to get to go figure this information out for everybody. So I think it's incumbent on all of us as academics to find avenues, whatever they may be, of sharing that information with not just other academics, but with everybody.
Right, and even it could be for, you could call it maybe like more selfish reasons of like, if you disseminate, then more people would get interested in your thing and whatever. And if your thing is, if you care about your thing, then it will grow and it would get maybe more money, it would get more attention, and more people would contribute to it, and more cool stuff will be happening.
Certainly that's true. I mean, if there's one thing we are hampered by, it's a diversity of thought. And, the more people we can reach and the more people we can engage to think about things, the better.
And what would you do to the people listening? What would you do? What would you say or advise to the people listening? Maybe if that person is maybe considering physics, or even if that person's already in physics and it's on its way, what would you say to those kinds of people?
It's gonna sound bad, but figuring things out that people have never figured out before is hard, right? The Earth is 4 billion years old now. People have been around for thousands of years. People have been staring at the sky for as long as they've been around, for just in the field of astronomy, but in any field this is applicable. Figuring out things no other humans figured out is really hard. And so the path is hard. You learn, in just an example of physics and astronomy, you have to learn very complicated stuff as an undergraduate. The math and the physics you have to learn is very complicated. And if you go on to graduate school, the stuff you learn is even more complicated. And then the longer you stay in it, the more complicated and difficult it gets. And the problem is that we are trained in society to say, if you are not understanding everything, if you are not excelling, there's something wrong with you and you don't know what's going on. And the advice I would have is to say that's not the right way to approach it. I think the right way to approach it with your own mentality is to get comfortable with the unknown and get comfortable with the difficulty of it and say, it's okay that it's hard. It's okay that it's unknown. And that's why I'm here, is to figure that out and to contribute to that and to learn. And so, yes, it's hard, but it's hard for everybody. No one's out there making it. There was one Einstein, literally. I mean, it's for the rest of us, it's hard. And I think it was probably hard for Einstein too. It was 100 years ago. Who knows? And so it's okay that it's hard, and it's going to be hard. It doesn't mean you're bad at it. It just means you're trying something really hard. It's like asking Usain Bolt, was it hard to be the fastest human on the planet? Well, of course it was hard for him. But it was hard for everybody. You're trying to push the frontier in your own way, whatever your field is. If your field is history, if your field is mechanical engineering, if your field is astrophysics, you're trying to figure stuff out that no one's figured out before. So of course it's going to be hard, and don't let that deter you. I would say, just get comfortable with the fact that you're working on things that are cool, and as long as you think they're interesting, then who cares if it's hard?
And I think final question: Why is the meaning of life 42?
That's the wrong question. The question to ask is, what is the question? You got lucky. I happen to just have read that chapter of Hitchhiker's Guide to the Galaxy last week to my son, and then yesterday I was on a run with my wife, and she's never read these books, and I was trying to explain to her how the Earth is really a big computer trying to figure out what is the question that leads to the answer 42. And she was like, "You're such a nerd. This is not."
And on that note, final question: what are you grateful for? Grateful for, Desika?
I'm grateful for the opportunity to get to come to work every day and work on cool problems and get paid for it. I mean, it's crazy, right? Like I said, the stuff I get to work on is the only thing that's cool about it is that it's cool. It doesn't make your life easier in any way. But I'm really grateful for the fact that we have, as a society, deemed it valuable, just the exploration for new knowledge. And I'm grateful that we, as a society, pay for that and value it. And I hope to be able to keep continuing doing it forever.
Thank you.
Thank you. Why are you reading that Michael Crichton book? What value is that to you? Well, you're learning something. You're expanding your mind. You're thinking different. Who cares? Why? Just because you enjoy it.